So hello, and now what we are going to do today is to go back from differential back to integral calculus, and in order to do that we need one result, basically one result, which is known as Lagrange Theorem, but we will prove it in the framework of a set of theorems that I like to call the four little French theorems. And probably all of you know these theorems because they are studied and also proven in general also in high school, and the theorem are due to Fermat, but this is not the big famous theorem by Fermat. Cauchy, Rolle is before Cauchy, and Lagrange. Lagrange was not French; he was Italian from Turin. So I put French here under quotation mark, but I like to call for little French theorems because everybody in the world is convinced. Also, my colleagues are convinced. My colleagues, not Italian colleagues, but colleagues from abroad are convinced that Lagrange was French. Indeed, he was from Turin, then he went to Berlin, and then at the end of his career he went to France, where he became really famous. I heard that he is the only non-French which is buried into the Pantheon in Paris. And however, there are various testimonies that say that wrote that lectures by Lagrange were very good, except that his Italian accent was really horrible, was too strong. Okay, so we start with the theorem by Fermat. The theorem by Fermat talks about extreme points, in particular maxima and minima, and I want to specify a bit better what is a maximum and a minimum. We just know what is global or absolute value, absolute maximum and minimum, but there is also another notion, which is the notion of local maximum and local minimum. So the first definition I give you is the following. Let us consider a function f. It is comfortable to consider f as defined on an interval, and let me take it as closed, for instance, but it is not necessary. From AB to R, we have x bar in AB, closed, is called a local or relative maximum point if there exists a neighborhood U of x bar such that for every x in U and also in the domain of f and AB, we have that f of x is not larger than f of x bar. Okay. Moreover, f of x bar is called a local or relative maximum. The definition can seem to be contradictory, but indeed notice that the point x bar, is a local or relative maximum point. There is also the word point, and on the other hand, f of x bar is local or relative maximum. Okay, so as a picture, in order to clarify this notion, we can think of a function like this. So start and so it is not necessary to. So it is not necessary to make it continuous, but I want to make it continuous. However, what I'm saying here that local maximum is a point that is a maximum of the function restricted to some neighborhood. Okay, of course, intersection with after the intersection with the domain. So for instance, this is a good neighborhood here where the point, this first point here, is a local maximum, and here also there is a local maximum. And for instance, here notice that this is a local or relative maximum point. And this is a local maximum. And here again we have a local maximum point and local maximum, and this is, again, it is a local maximum point, but also a global maximum point or absolute maximum. Why? Because this point here is not only the maximum on some neighborhood of x bar, but it is a maximum of the whole function. Okay? The others local maxima are not, but notice that here. This is also the global and also local maximum. Okay? So in particular, a global maximum is also a local maximum. Of course, there are other points here which are minima just in a neighborhood, and so they are called local minimum, and this here is a local minimum point. And here, on the other hand, we have a global minimum point. And this is a global minimum. So we can give another definition here. The definition of minimum, we can say that given a function f in AB, a point x bar in AB is called the local or relative minimum point if there is a u in ux bar such that for every x in this neighborhood u of x bar, but also in the domain AB of the function, we have f of x is less or equal, and here larger or equal f of x bar. And of course, f of x bar in this case is called the local or relative minimum. Okay? You know, when a function represents some natural phenomenon, think of sad things like people who are infected by COVID, and you always hear people saying, okay, now we are at the maximum, we are at the plateau, or we overcame the maximum, fortunately. And so finding where are located maxima and minima is extremely important in the study of natural phenomena. For the COVID, it means that, okay, now the phenomenon is declining after the maximum. Of course, if people behaves well, on the other hand, when the maximum was not reached, for instance, in the number of deaths, daily number of deaths, it seems that we are still not at the maximum, even though the number is very high. And this is very sad because it means that the function is going to climb up a bit before starting diminishing. Okay, so it is important. And from the point of view of the analysis, there is a tool which is powerful in order to find maxima and minima, and it is simply the derivative. How? It is the theorem by Fermat that explains that. So this is a theorem by the famous Pierre de Fermat. And let me state it in the following way. F from AB to R. Again, here it is not really necessary to have a closed interval. But and the important fact is that X bar is an internal point. So it is in the interval, but it cannot be A nor B. This is a maximum point, a relative, a local relative maximum point. Then, moreover, F is differentiable at X bar. Then, and this is the important statement, F prime of X bar is equal to 0. So very, very roughly and briefly speaking, we can say that the derivative vanishes in point of maximum and also of minimum. But recall that theorem always has hypothesis, and here the hypothesis that first of all X bar is an internal point, and second, F is differentiable at X bar. So here is the proof. So since X bar is a local maximum point, then it means that there exists a neighborhood of X bar such that for every X in U intersection AB, we have f of X not larger than f of X bar. Now, consider a point X in this neighborhood, U intersection AB, and X larger than X bar. And then look at the incremental ratio means that f of X minus f of X bar divided by X minus X bar, and these signs are positive at denominator and, strictly positive at denominator, and non-positive, so less or equal 0, at numerator. So the ratio is non-positive. Then when we perform the limit for x going to x bar from the right of the incremental ratio, f of x minus f of x bar divided by x minus x bar. By permanence of sign, this will be less or equal than 0. But since the derivative exists, also the limit, the whole limit, and not only the right limit, exists. And it must be equal to the limit from the right, because we studied that when the limit from the right and the limit from the left, the three of them exist, then they are all equal. But this limit here is f prime of x bar, because the derivative exists. Then we put all together here, f prime of x bar is non-positive. And this is formula 1. Analogously, consider again x in U intersection AB and x less than x bar. Then, again by incremental ratio, we have that the limit, we have f of x minus f of x bar, x minus x bar divided by x minus x bar. And again, the numerator is non-positive because f of x bar is a local maximum. But this time, the denominator is negative because we took x less than x bar. So the incremental ratio is non-negative, and again, by permanence of signs, as before, we have that the limit for x going to x bar from the left of the incremental ratio this is not less than 0, but again, as before, this means that f prime of x bar is larger or equal than 0. So from 1 here, derivative non-positive, and 2, derivative non-negative, we have that the derivative must be exactly 0. And okay, of course, the same result and the same proof, analogous proof, hold for minimum point 2. So again here I can change Fermat theorem just stating that instead of the maximum here, we compute minimum. And so let me give you some comments. First comment, the hypothesis that x bar is an internal point is necessary here. Because if it is not an internal point, for instance, consider f of x is equal to x squared for x in the interval 0, 1. 1 is a maximum point, is a local, also global. But f prime at 1 is equal to 2x computed in 1, which is equal to 2, which is different from 0. So it is not possible to extend Fermat's theorem to this point, and let me draw a picture in order to understand that. Okay, this is the parabola, this is 0, this is 1. And you see the tangent here. The tangent here has not angular coefficient equal to 0. The tangent at 1, 1, at point 1, 1, has not angular coefficient equal to 0. Second, probably it was better to tell before, but however, indeed, Fermat theorem say that the tangent, whenever it exists, this is the hypothesis of derivability, differentiability at x bar, whenever it exists, at the graph to the graph of a function at an internal minimum or maximum point, is horizontal again. Let me draw a graph here. Picture here is okay. Here we have maxima, minima, and see that the tangent is horizontal. Here, 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 and here too. these are all horizontal tangents. So another comment is the following. The theorem is not invertible. Namely, x bar in AB and f prime of x bar equal to 0 does not imply that x bar is a local maximum or minimum point. An example is given by f of x equal to x cubed. Take x bar is equal to 0, so you have f prime at x bar is equal to 3x bar squared, which is 0. But, of course, for every x less than 0, you have that f of x is less than 0. So here 0 seems to be a local maximum point, and for every x larger than 0, f of x is larger than 0. So 0 cannot be a local maximum point, nor a local minimum point. And so look at this. This is the graph of x cubed, and so you see that here you have a horizontal tangent, so x-axis is equal to tangent to the graph of f at 0, 0. The tangent is horizontal, but zero is not maximum or minimum point. So we saw it analytically, geometrically, and so on. And here we give another definition, just a language, just a glossary. Minimum a maximum point or a minimum point is said to be an extremum point. Okay? And then the next theorem will be a whole theorem, but I need another video for that.